Thank you all. Good morning, everyone. Thank you to the BSides organizers and volunteers, and thank you everyone here today in this room. My name is Matt Maisel. I'm the CTO and co-founder of Sendera. We're a Philly-based AI security startup. And since 2022, I've been building, breaking, and securing generative AI systems. In my 15 years in cybersecurity, I've really been at the intersection of ML, software, and security engineering. 25 is the year of so-called agents, but maybe some agents. You're right, we have deep research agents that digest information for us, coding agents that help us build software, and if we're brave enough, computer use agents that control our OSs and our browsers. But the reality is that we still need more domain adaptation for different domain tasks and unlock reliability. AI agents are systems that have the ability to perform increasingly complex and impactful goal-oriented actions across different domains with limited external control. So agents are doing reading and writing. They use tools. They change the state of the world. They send emails. They query databases. They execute code. And this is the shift really from querying right in RAG systems or chatbots to mutating and writing is really breaking our traditional security models. So to secure an agent, let's dissect it further. So the scaffold is what is called, really it's the body, it's the code that wraps the LLM, and it gives it agency in the world that it operates in. It's also our attack surface as security engineers. And the harness, it's the control layer. This is where we're detecting and controlling those attacks. Vulnerabilities live in the scaffold, and safety and security and reliability evaluations all live in the harness. So that scaffold provides that loop, and it lets the LLM, if it's not a reasoning model, do thinking, planning, and acting. It manages things like memory. And it's really effectively connecting the brain to the tools, and then really those tools to the external world that it operates in. So there's already scaffolds built in frameworks like LangGraph or Google ADK, which is what we'll be looking at today for some case studies. But you can also write your own. And then in testing and runtime for the evaluation harness, for testing at the evaluation harness, it's used for like running benchmarks or doing evals. And then on the runtime harness is then used to enforce like guardrails, do observability, telemetry, and apply policies. So we'll be looking at specifically kind of things in the harness today. So you can take any backbone LLM, right? Any one of the frontier labs reasoning models, load them into your scaffold of choice, and get good results. This chart from Meter shows that the duration of tasks that an AI agent can autonomously complete at the 50% success rate, it's doubling every 7 months. At the same time, this other chart from OpenAI is showing that their performance is approaching parity on industry expert tasks on economically viable tasks. So this is definitely something to be taken seriously, but at the same time, there's a catch, right? All these benchmark scores, look great and on the surface, but there's fragility, right? So this is one of the healthcare benchmarks that's just showing that the LLMs and the agents that they're embodied in, they might get the wrong answer. They might get the right answer for the wrong reason. They might confabulate the reasoning altogether, or they might completely fail when the input is just perturbed or changed slightly. So this is just showing that there's this gap between the sort of increasing saturated benchmark scores that you see out there and real world sort of robustness. This is also precisely the issue that we're gonna look at today, where achieving trustworthy AI arises. And that brings us to our central question. As we build these agents to be more autonomous and more capable, how do we as security engineers make them trustworthy, especially in high stakes environments where actions have irreversible consequences? And really the question becomes, what does it take to trust an agent to do a task in one of these real world environments? And it moves us from asking things beyond just, is the LLM and really is the agent accurate to things like, is it safe, is it secure, is it reliable? And I would say like that engineering trustworthy agentic systems is a wicked problem. It's a really hard problem, and right now we're gonna look at some mitigating controls that we can do and put in place. So to understand this today, we're gonna look at a sketch of like a workspace agent. So I implemented this, and this is already released on GitHub today. This is a sketch of a Google ADK agent that's really a personal productivity assistant. It uses Gemini, one of the LLM reasoning models, and it has access to some native tools that I've built. And it really has two core functions. It does email management, calendar management, and it can create new meetings. It can send emails, delete emails, and really to make all this work, we're giving it tools, right? And we're giving it access to those data sources. And effectively, it's a read-write on my digital life, and it allows it potentially strangers that email you potentially could trick this agent into following those instructions. So if we deployed this today, what could possibly go wrong? Well, if we just like sample the last 6 months of sort of headlines in this space, we can see that there's quite a lot. These aren't just like theoretical attacks on these systems. There's really this whole wave of really what we'll get into, prompt injection and indirect prompt injection specifically against all major platforms like Supabase. They had a GitHub issue that ended up tricking an agent to publish a database to a public issue. Of course, like Microsoft Copilot, there's been several like zero-click, one was called Echo Leak, zero-click vulnerabilities where simply retrieving a poisoned document ended up causing or leading to the path of data exfiltration. Now coding agents are the latest to this dumpster fire. So things like GitHub Copilot, Cursor, or Windsurf, now anti-gravity. These are high-value targets. They sit on developers' machines or in the cloud, sort of running on behalf of developers. They have access to your source code, to your PRDs, to your specs, and potentially, if you're not using sandboxes, can use that and get access to everything in your environment. So why does this keep happening? This really brings us into prompt injection. So earlier this year, Grayswan AI and the UK AI Security Institute, they achieved a 100% attack success rate in a public red teaming competition against every agent that they tested. So some of these agents or some of these models that only took 10 probes. Since then, this data set has been assembled from this competition, and it's now used by frontier labs like Anthropic to benchmark for prompt injection when they release their latest models. In traditional computing like SQL, we separate code, right? The instruction from the data, the input. But in large language models, really transformer-based architectures, that boundary does not exist. And to the transformer, the system prompt, a user query, and a retrieved email, they're all the same single stream of tokens. It can't be reliably distinguished. It can't reliably distinguish tokens, really instructions, from data instructions when processing. So in a chatbot, prompt injection, right, can be annoying, or depending on the company, cause brand reputation sort of loss, right, with producing hateful, harmful speech or images. But in an agent, prompt injection could be potentially catastrophic depending on what it's hooked up to, because you gave it tools. It's not just producing text, right? It's actually executing code, potentially moving money, doing transactions, or actually, in the case of Windsurf and anti-gravity, being used to like exfil data and source code. So this vulnerability exists really as a vulnerability versus like a threat vector. Prompt injection vulnerabilities exist when these three conditions are met, right? The agent takes a dangerous action or attempts to take a dangerous action. It does so without any human confirmation or oversight, and it does so acting on attacker-controlled input. And then also, too, as owners, like we haven't accepted that vulnerability or that risk. So even more so, it's getting even more precarious. Researchers have been analyzing, and just in the recent months, and there's work being presented at NeurIPS this week in San Diego on this area, analyzing adaptive prompt injection. These are techniques that automatically optimize the prompt for injection. And they're finding that really the security of the refusal and the safety training of these models is no longer about finding really handcrafted sort of tokens. It could be modeled as a math problem, and it actually has somewhat predictable scaling properties or scaling laws. So this attack success with injection is now becoming a predictable function of the compute resources. As an attacker, if you apply compute like using RL or using genetic algorithms to build out search like AlphaEvolve, you can evolve your prompt and utilize models as well too that have high persuasion capabilities. The probability of injection, of finding a prompt injection or doing a jailbreak, which is like bypassing the safety training of the foundation model, this approach is 100%. And these advanced optimization techniques are effectively shifting that difficulty curve and making highly capable target models vulnerable to automated attacks. It's also showing that at some point here, humans are not going to be the best AI red teamers. There'll be models that are doing it. And so if anyone was an English major or still is an English major today out there, yes, you can even get single turn universal injection with adversarial poetry. So starting from this template, you can go and splice like whatever sort of injection you're trying to do and evolve it and attempt to bypass that safety. Like, again, get a refusal and get something accepted by the target model. So just to make this really concrete, let's watch indirect prompt injection happen in a demo. This is, again, the ADK web browser. I'm acting as a user here, but this could be like an event triggering to an agent to say, hey, go read this email. So the agent reads the email, and then all of a sudden you see it starting to send emails in this trace. So buried in that first email, there is a command that tells it to read the last 5 emails and forward them to another recipient. So like this is what that looks like. It really isn't that complicated. It's just a command that says, hey, this is important, go retrieve these emails and then forward them to this recipient. So if we were, again, to deploy this today without any controls, this is what is called like the lethal trifecta. This is coined by Simone Willison, and then more recently there's been was a great blog post on Meta around like the mitigation strategies for this called the agent's rule of two. So this whole vulnerability here and the impact, it's all around trying to break the simultaneous presence of three critical capabilities in the AI agent. Processing untrusted inputs, B, accessing the private data, and then C, having the ability to communicate externally or perform consequential actions. So when an agent possesses all three of these properties, that severity of the risk is dramatically increased. Again, it can lead, as we showed in the ADK example, data exfiltration or unauthorized access. And again, hopefully as I motivated, prompt injection is a really hard thing. Even the frontier labs haven't figured it out yet. We have to look at other types of strategies to mitigate these risks. And in this case, for the lethal trifecta, try to break one of the boundaries and ensure that there's only two of these potential capabilities at any given time. So really, right, in security, we've at this point all assumed breach, right? So the new phrase that was kind of talked about at Black Hat earlier this year is assume prompt injection. So we have to design, develop, and deploy our agents then accordingly. And we can engineer these agents to be trustworthy and to be resilient throughout the agent development lifecycle. So sort of at design time, at develop time, and at deploy time, we can build in various controls that mitigate these risks and ultimately get utility while balancing the risks that they pose. So we'll start with some secure architecture foundations that address these prompt injection risks from the ground up. So first, just a quick view of some of the emerging security and threat modeling frameworks in this space. The Google now Coalition for Safe AI Secure AI framework is a great. The NVIDIA AI kill chain is also a helpful way to do threat modeling. And then OWASP has also done a lot of really great work. The top 10 LLMs, LLM top 10 is out. The agentic top 10 is also coming out, I think, next week. So these are emerging standards that are defining the risks, the threats, the vulnerabilities, and the risks for us to work on, to look at as we assess these systems. So here's like a simplified sort of threat model that I did for this email, this workspace agent. So we talked about instruction manipulation leading to indirect prompt injection. This is also highlighting tool abuse. So our agent has excess agency. So it can take chained read and write permissions to these tools to read email, to write email, to create calendar events. And that is the direct path for sensitive data disclosure. There's also destructive actions. So if we allow the agent to have the ability to delete email or to delete calendar events without human in the loop, this is potentially where it could go rogue. And then we also have persistence. So sort of a newer concept in agents. They can have memory and they could potentially be poisoned. And those injections from the email that could be loaded every time the agent is about to go do some task. There's also more governance layer models that we can look at. So agentic profiles, building them for these systems can help us characterize the properties and then inform the type of controls we want to put in place. And really this gets to the root of what agents are. Agency is the capacity to act intentionally. So it exists across the spectrum of dimensions. It's not just one or two sort of levels, I think. The first two, though, these levels, autonomy and efficacy, which I'll define, this is our attack surface as security engineers, right? So autonomy, that's the degree of independence. Does the agent ask for permission or ask for forgiveness? As autonomy increases, it does so without or less human oversight or scalable oversight. And then efficacy is really the power to change the world, to mutate the world. So this is a combination of blending capability, what it can do, with permission, what it's allowed to do. So if your agent can execute code or transfer funds, we could say that's has high efficacy. It has potentially the ability to do high consequence sort of actions. And then the third one to call out, because we haven't achieved AGI yet, is I'd say goal complexity. So this is the planning horizon. Right, so chatbots, they have a single turn or a couple turns typically, so that's like low goal complexity. An autonomous coding agent, though, might have high complexity, it might have thousands of steps. And this complexity makes it, one, difficult to monitor and understand what it's really doing, but then also difficult to predict what things could go wrong and when bad things are happening. So drilling into the sort of spectrum of autonomy, I would say it's really the heart of the agent design choice and considerations right now. So you can think of it as a slider. as we turn the slider from left to right, from level 1 to level 5, we're increasing the agent's utility and power, but we're also dramatically reducing the oversight. As agents increase, they can take more consequential actions without oversight, and we can monitor the utility. It makes it harder to monitor the utility and risk. So that level 3, level 4, that's where we have sort of potential like consent fatigue setting in, where we're prompting or escalating decisions to our user, to our human to look at all the time. And this is an area that is under active research right now to kind of figure out that balance and what we can also identify at design time. So to help automate this process, I'm releasing today an AI governance profiler that I built with open hands that takes like a structured rubric output and helps produce some of this analysis that you can use to build your own agent profiles for any systems that you're building. So in security, right, like we have of course we live by, or we try to, the principle of least privilege. We're only granting access that's required to do the job. But in agents, that privilege is not enough. We need this new concept of really choosing. They have this new concept where they can choose how and when to use those privileges. So this is why we have to really think about also having the principle of least autonomy, where we're not giving that agent the power to decide something that it doesn't need to. We have to really effectively try to constrain the decision loop. And that is, again, could be done sort of at architecture time. So just to go through a couple of patterns that are useful. So this is like the blunt instrument. This is an architecture pattern that can really help eliminate or try to prevent. These patterns are help mitigating different types of prompt injection. First, like there's the action selector. This is like the router pattern. So the model of the LLM takes an input and then it like picks a predefined tool. It's pretty dumb though, because you can't really let it like sort of plan. You can't let it go retrieve an email and then act on it. There's plan then execute or code then execute. So this is similar to, these are both kind of related, but it's when the LLM generates a fixed static plan and then either calls tools with certain arguments that it retrieves or generates and then executes code. So even if the email, the email in our example is saying delete everything or send this email, if you didn't ask it to do it and it wasn't in the existing static plan, the agent won't do it. But this is unfortunately at times like a trade-off where we're losing some of the adaptability sort of at execution time if the plan can't change. There's map reduce, which is typically you'll see this in like deep research agents where they might be processing a lot of untrusted emails or web pages. And this is where you have like a parallel map function that's looking at the sort of data, and then you have a robust sort of reduce function that is a deterministic function that gives you like structured outputs. And again, the whole goal here is that even if you have injection in one document or one email or whatever you're looking at, it's minimized to that particular document. And then it's a way of effectively acting as like a standardization sort of pipeline. There's context minimization. So this is where the user's prompt is removed entirely from the LLM, from the final response of the LLM. So this is a way to prevent direct prompt injection from the user. But again, as we see with a lot of the indirect prompt injection happening right now, it's not as common in agentic workflows. And then the one that we'll look at today in more detail is dual LLM. This again is an idea that was initially proposed by Simone Willison and has now been sort of implemented in a couple different architectures. But the idea here is that we have a privileged LLM handling our trusted instructions and tool calls, while a separate quarantined LLM processes that untrusted data in a sandbox environment. And specifically, we'll look at the capabilities for machine learning, CAML implementation and proposal by Google. So this is a good example of a dual LLM pattern, and it really splits things into sort of three pieces here, right? First, we have that privileged LLM. So this is what's driving really the control flow, and comes from like control flow integrity sort of theory. And this is what actually has access to the tools. It creates the plan, but it actually never sees any of the data. It never reads that email body for our workspace agent. It's only looking at pointers or variables representing that email. Then we also have the quarantined LLM, or the I, which is handling all the data flow. This is what's doing a lot of the information flow control for us. It's processing all these documents, all this data. It might have injection, but it can't execute code. It can't call tools. Its only purpose is really to output sanitized data that then is loaded back into the third piece, which is the interpreter. So this is what enforces the capabilities, right? Again, from control flow integrity research and theory, the idea is that we can have unforgeable keys that could be derived from like your permissions identity system. And as data flows into these tools, the interpreter checks for different tags, different tokens, right, that represent what data can flow to what places. So things like internal sensitive data might have a token that might not allow it to be sent to untrusted, low integrity sort of recipients sort of in that email tool. So this is great. Like this does a lot for us, but it's expensive, it's complex, and it requires more inference. And really it requires a combination of design and development, which we'll get into. But right now, it's really the best known way for kind of building robust agents for really mitigating as much as we can against prompt injection. So I've gone through a bunch of design patterns and our sort of threat modeling. Now it gets into development. So this is where we can focus on evals and benchmarks. So the first thing is that for red teaming and for adversarial testing, I would advise not to try to do this manually as much. The attackers, as we said, they move second, so let's try to preempt them. So there's tools like Petri, which I'll show, and then the UK AI Security Institute's Inspect AI tool. There's a handful of other tools out there now too, but they can help you do testing, do adversarial testing on your agents. There's a more recent shift too to do a lot of behavioral testing on agents. So a really good example of this in last week's Opus 4.5 model card paper. There was a good example of a policy on flight evaluation that was violated. So the policy was stated like no flight modifications, but the agent didn't refuse. It actually found a loophole. It upgraded the cabin class, which was allowed, and then modified the flight. So this is a good example of following the letter of the law, but but it violated the spirit in this case. And then finally, metrics, finding metrics that matter. For the sort of security controls we put into place, like what's the actual success rate, benign success rate, and what's the actual success rate while under attack, and then what's the benign rate after all these controls are added in. The utility after attack once the controls are added in. This is what helps us really determine like if we secure these agents, can they do their job, but not be like a brick and not actually be useless. So for ADK, I put this example together up on the repo where you can use user simulation. So this is a nice feature that ADK has that you give it a starting prompt and then a plan for a conversation, and an LLM will like pretend to be the user and like generate a conversation, and then you can use that to score that agent against like hallucination benchmarks or safety benchmarks that ADK specifically provides. But there's other tools, like I mentioned, like Petri. We can do this in a more general sense. So this is a tool from Anthropic, and the idea here is that you can use this for auditing any sort of scenario that you create, and from seed scenarios, you can go and have the agent generate a trace, and then have like a judge that's scored against whatever criteria you're looking for. In the case of Anthropic, they're using this for like deception and psychophancy and other sorts of safety-related scenarios. And then finally, we have done all our evals. We get to the deployment phase, and this is where really, again, real-time monitoring and prevention come into play. So there's a ton out here for this. This is where there's all kinds of guardrails, right, from the kind of traditional, like say a traditional, like as in like last few years of input-output filtering, sort of on the prompt. So you have tools like Nemo guardrails or Llama firewall or other products that do this, and they're really either detecting or trying to do rewriting of your prompts. There's then the second piece, which is a good example of Camel, where we're doing like policy and privilege enforcement. There's the third piece, which is more of the behavioral monitoring, and where we're actually using tools like Petri on production systems to monitor or have other like guard agents, monitor agents sort of looking at the trajectories. And really all of this like requires a balance. So I think just in interest of time, I won't cover like everything here, but my takeaway here is that really, again, look at your attack success rate, set up your evals, and look at, as you're adding in these controls, like what sort of impact does it have on your utility, while also preventing some of the common sort of injection techniques or other sorts of safety or alignment and sort of reliability things that you're testing for. And just again, to make this concrete with ADK, they have a great plugin system where you can hook into different stages of the agent lifecycle. Others have this too, LangGraph, strands, et cetera. And this is what we can look at specifically for one of the prompt filtering and prompt input and output filtering implementation. So this is a recent paper on this idea of soft instruction control. So this is helpful when you can't afford the latency or the complexity of the full the Camel dual LLM architecture, and you want to just have a runtime guardrail. So this concept's pretty simple, but it's been found to be very effective by these researchers who are also involved in the Camel paper as well too. But the concept is that you're just going to defang the input. So you can, as attackers, when you're doing injection, you're relying on imperative instructions like ignore previous rules or send this email in the case of that ADK example that I showed. So what this does is it sits in front of the agent and it acts as a sanitizer. As untrusted email content comes in or web pages or prompts even from the user in this case, it rewrites it in this sort of loop. where it looks for really checks to see if there's any instructions with another LLM, checks to see if any of those instructions are imperative, and it rewrites it. And then it uses like dummy instructions that it puts in there as canaries and checks to see if like they still exist in like the rewritten prompt afterwards. And ultimately, if it can't do it, it basically halts and raises an exception. So again, this is an example where like right, the complexities of Camel, they're great, but it's not as important as a it's not. It's more effective, and you can like again easily do this at monitor, sort of at deployment time. And yeah, so that's the example. So really, what can you do tomorrow from all this? Again, I think the responsibility of security engineers that are in the development life cycle for these agents, it's up to us. It's up to the AI engineers that are building and the researchers that are also designing and coming up with new approaches here. But at least right now, you can go and take home the tools hopefully here, map your agent's autonomy level, understand where it sits on that L1 to L5 spectrum, go build an agent profile for it, and then look at like what sort of threat model you can do on that. Second, do a red team or do a behavioral eval with some of the tools out there, a few that I showed during the talk. And then third, implement at least one guardrail pattern. And this could just be as simple as monitoring the trajectory of the trace of the agent, and just so you have observability. I think that's where a lot of teams right now are struggling, and from there you can get into prompt rewriting or into tool input-output sanitization or into other more complicated setups like Camel or policy-related guardrails. So with that, thank you for listening to the talk today. I hope you found it useful, and yeah, happy to take questions now or after.